Hello there, Mr. Sutton here, bringing you the AB Calculus 615 Extra Practice number 4 solutions on integration with respect to the y-axis. For this one, we want to know the volume of the solid generated when the region in the first quadrant, bounded by this graph here and the x and y-axis, is revolved around the y-axis. Well, let me start by graphing this thing out. So there we go. I've entered this into y1. Not really sure what window I'm going to use, so let me just do zoom 6. That'll give me 10 in every direction. It's a good place to start. So we basically have a semicircle, or something approaching that, and I'm just going to kind of connect it to the x-axis here, because it does connect. It's just weird the way it graphs things with these semicircles. So anyway, I want to revolve the region here in the first quadrant around the y-axis. So I know that at some point I'm going to be integrating with respect to y. In order to prepare for that, I'm going to rewrite this function here as x equals something that's a function of y. So this is going to be a little bit of a chore in the beginning. Let me start by squaring both sides of the equation. So I've got y squared equals 100 minus 4x squared. And then let's see here, I can subtract 100 from both sides. And while I'm at it, might as well divide by negative 4. So we have y squared minus 100 over negative 4. And then I need to square root both sides to get x truly by itself. So while I'm doing this, I'm also going to take I'm also going to rename this function. I'm going to call this f of y. So this is just going to be x equals the square root of all that stuff. All right, now that I've got that renamed, I need to figure out my limits of integration. So I need to figure out basically, I already know we have 0 for the lower limit of integration for the y value. The upper limit, it's going to be wherever this x value coincides with the x value 0, wherever we're hitting the x-axis, the y-axis. So just thinking about what I would need to zero this thing out, if I made y 10, 10 squared minus 100 would be 100 minus 100. That would zero it out. So y equals 10 is my upper limit of integration. So now for the area I'm going to need on this, since I'm flush against the axis of revolution with this area, I can just use discs on this one. So a of y equals pi r squared. And then r in this case is just the distance from the y-axis, the axis of revolution, to this curve. Well, that distance is just given by this f of y function I just created and named. So I can write this as pi times f of y squared. And on the calculator now, I'm going to do the integral from 0 to 10 of a of y dy. So let me try that out. To make things a little bit easier for myself, I'm actually going to do some work in the y equals. So I'm going to enter this function in terms of x in my y equals. So I have a square root. Let me do fancy fraction here. And I'm going to do x squared minus 100 all over negative 4. Inside a square root, and then for y3, I'm just going to do my a of y function. So that's going to be pi times alpha trace y2. That's the f of y function right there, and I'm going to square that. Quitting out of there now, let me actually do my integral after all this. So math 9, we're going from 0 to 10, and now I'm going to do alpha trace y3 to bring up my a of y function. And although all of that's in terms of x, I'm going to make that okay by making this d a dx. So now my calculator will just treat it like we're treating the y down here. It's just a dummy variable after all. So we end up with 523.599 for that one, which ends up being answer choice B. On this problem, R is the region between the graph of y equals ln of x, the x-axis, and the line x equals 5. We want to know which of these gives the area of region R. Let me start by graphing this out on my calculator. So there's ln of x, and let me do zoom 6 to get that in there. Let me also graph out the line x equals 5, so I can quit out of there, and I'll use the draw menu, second program. Option 4 gives me vertical, and I need a vertical line at 5. All right, so that's a picture of what I'm dealing with here. Now, if you look at all the answer choices, they are all integrated with respect to y. So it would be much easier to actually do this with respect to x, because my function's already in terms of x. But if I want to integrate with respect to y, I need to convert this, rewrite this. So basically isolate x. Now to do that, I have to raise e to both sides, so I can rewrite this as x equals e to the y. And now I have to think about this. Instead of going from left to right with my limits of integration, I have to go from bottom to top. So on the bottom, we definitely have y equals 0, but how about the y value right here? So basically, I need to figure out where e to the y equals the x value 5, where these intersect in terms of y values. I can do that by just setting this equal to 5, and then to get y, I just have to take the ln of both sides. So y is going to be ln of 5. So then my area of this curve, we're going to have the integral from 0 to ln of 5 of. Now inside here, I'm not doing with respect to x anymore, so it's no longer top minus bottom. Since I'm doing this with respect to y, I have to do right minus left. So in this case, that's going to be the function 5 minus this function of e to the y, and we have a dy in there as well. And that ends up being, let's see here, answer choice, is that going to be C? Yep, choice C. For this one, we're told R is the region in the first quadrant bounded by y equals radical x minus 1, the x-axis, and vertical line x equals 10. Which integral gives the volume of the solid generated by revolving R around the y-axis? All right, so let me graph this out. Let's see here. Here's my x and y-axis. The line radical x, or the graph of radical x minus 1, well, this is just a square root function, but we're shifting it right 1 if you remember your transformation rules. So this is going to look something like this. And we also have the x-axis forming one of the boundaries of our region R, and the vertical line x equals 10, which is going to be somewhere out here. So this is the region R, and we're revolving this around the y-axis. So I know if I'm trying to find volume, I'm going to have to use an integral. I'm going to have to integrate some kind of area function. For my integral, since I'm integrating with respect to the y-axis, revolving around the y-axis, I have to get all my functions that are involved here in terms of y. So this y equals radical x minus 1, not good enough. I have to make this x equals something with y in it. I can do that by squaring both sides and then adding 1. So this is really x equals y squared plus 1. And for integrating, I also need limits of integration. So integrating with respect to y, I need the lower and upper limits to be y values. So on the bottom here, the lowest y value for this bounded region is going to be 0. And up here, what's the y value up here? Well, I need to figure out where y squared plus 1 equals this x value of 10, because that's where these two lines are going to intersect. So that's going to happen if I subtract 1 and square root at y equals 3. Also negative 3, but that's clearly not negative 3 up there. All right, so now I need to figure out the area function. Well, because I have this gap here between my bounded region and the axis of revolution, that means I have to use washers rather than disks for my revolution cross-section. So I'm going to write a of y equals pi times big R squared minus little r squared. Big R is going to be the distance between my axis of revolution, which they said was the y-axis, and the further away part of the bounded region, which is the line x equals 10. So my big R is just simply going to be a constant value of 10. For little r, that's the distance between the axis of revolution, the y-axis in this case, and this closer function. So that's going to be, let's hear, just y squared plus 1. Now plugging it all in, I'm going to need the integral from 0 to 3 to get the volume. Integral from 0 to 3 of, and now I'll put basically all this stuff in there. So pi times, this is going to be 10 squared minus y squared plus 1 quantity squared dy. And this almost matches some of the answer choices, but not quite. To match an answer choice, I'm going to clean it up a little bit. One thing I'm going to do is pull this pi outside. And inside, I can square that 10 to get me 100, and there's really nothing else I need to change in there. So that's going to end up giving me answer choice D. For this problem, we want to know the volume of the solid generated when I take the region in the first quadrant, bounded by x squared, the y-axis, and y equals 1, and spin it around the y-axis. Let me draw this out to get a little bit of a visual of what's going on. So here's my axes. And I've got just a piece of x squared. I'm just going to draw the part in the first quadrant, so it's like a half of a parabola here. And then we have the y-axis is one of the boundaries, and also the horizontal line y equals 1, like so. So this is the region here, and we're trying to spin this around the y-axis. So in order to do this, I need to write things first off in terms of y, if I'm integrating with respect to y. So this y equals x squared, let me rewrite that as x equals the square root of y. And I also need to get limits of integration, because I know for volume I have to integrate area. So these are going to be y values now. I'm going from bottom to top. At the bottom, we have the y value 0 here. At the top, well, they already kind of gave us this. This is the y value 1, because that's the horizontal line up there. So I'm going from 0 to 1, and now I need the area function as well. Since this is a solid of revolution, I'm choosing between disks and washers. And because my bounded region is flush against the axis of revolution, which in this case is the y-axis, that means I'm going to use disks on this one. There's no gap in there, so I don't need washers. So I'm going to go with a of y equals pi r squared. My radius is just the distance from the y-axis, the axis of revolution, to the outer edge of that bounded region. So that's just a distance of radical y. It changes depending on the y value. So I can then write pi times radical y squared. And at this point, I've got enough to take an integral. So my volume is going to be the integral from 0 to 1 of basically this stuff. Now I'm going to save myself a little bit of trouble since I have to do this whole thing by hand. I'm going to save myself a little bit of trouble by pulling this pi outside my integral from 0 to 1. So inside, I'm just going to have the square root of y squared. But wait a sec. Radical y squared is just y. So inside, I've just got y dy. Let me take an antiderivative and use my fundamental theorem now. This becomes, 1/2 y squared, integrated from 0 to 1. And to save myself a little more trouble, I'm going to pull out this 1/2. So this is going to be pi over 2 outside. And inside, I'm just going to have 1 squared minus 0 squared. So 1 squared is 1, 0 squared is 0, 1 minus 0 is 1, times pi over 2 is just pi over 2. So a whole lot of nothing going on in there to get that result of pi over 2. So that ends up being answer choice C. For this one, we've got triangles on the brain here. R is a triangular region in the first quadrant with these vertices, 0, 0, 0, 2, and 1, 2. And then they're telling us this is the base of a solid. Before we go any further, let's just graph out what's going on here. So we've got the x and y axis, and I've got 0, 0, 0, 2, and 1, 2, so this triangle here. So now this is apparently the base of some solid. And for the solid, each cross-section perpendicular to the y-axis is an isosceles right triangle with the right angle on the y-axis and one leg in the xy plane. So basically, we've got these triangles that are oriented from left to right here, popping out of here three-dimensionally. And we have to basically, these triangles, when you put them all together, form some solid. We're trying to find the volume of that solid. So just thinking a little bit ahead on what I'm going to need to do here, there's a lot of steps on this one. At some point, my goal is to integrate some area formula over some interval. So in order to integrate anything, I'm going to need to express the bounding functions as, well, actually functions. So this line up here, this is just going to be the line y equals 2. That's just going to end up being one of our limits of integration. Since these triangles are perpendicular to the y-axis, that's code for knowing that I'm going to have to integrate with respect to y. So I know my limits of integration, I have to go from bottom to top here. On the bottom, we've got 0. On the top, we've got 2. So nothing super tricky on that. But I need some functions. At some point, I need to talk about this area in here. So this line here, the right bounding function, if I'm going up 2 and over 1 to get to the point 1, 2, this is just going to be the line y equals 2x. It's a slope of 2 going through the origin. So that's our right bounding line. The trouble, though, is if I'm integrating with respect to y, I can't just leave it in this form. I have to actually express this as x equals something with a y in it. So I'm going to rewrite this as x equals y divided by 2. So now I have something I could actually use to integrate something with respect to y. Going a little bit farther down this road now, I need to talk about the area formula that I'm about to integrate. Now, they said that the cross sections were isosceles right triangles with the right angle on the y-axis. So in general, I have a triangle area of 1/2 base times height, but I have to find a way to express this in terms of y in order to actually use it in an integral with a dy in it. So the key on this, if I just draw one of these triangles, they said it's an isosceles right triangle, so like this, with the right angle on the y-axis. So you can imagine this right angle popping out of the y-axis here. Now you'll see that if you draw it like this, and these are going from left to right, just like this picture, so it's kind of nice, the base of this triangle here is actually just the distance from one end of this triangle to the other. So if we can somehow rewrite this area just in terms of the base, that'll at least be a good starting point for expressing this whole thing in terms of y, because this base of the triangle is the only thing with any connection to y values. Okay, so since it's an isosceles triangle, an isosceles right triangle, that tells us that this other side here, the other leg, has to also be the same distance as this leg. So this is also a b up here, which means that I can rewrite this formula as 1/2 base times base, or 1/2 base squared. Now we have to talk a little bit more about the base. Since that's the distance from our axis right here to this line, I can write that as, let's see here, this line is actually, this x equals 1/2 y is just giving me the distance from one end to the other here. So I can just rewrite this as 1/2 times 1/2 y quantity squared, because this base is just this x value that you get when you plug a y value into this line. And at some point, I'm going to have to clean this up a little bit and integrate it. But I might as well just save that for the next step. So I can write now that my volume is going to be the integral from, we said, 0 to 2 of, and basically of this a of y formula. So now is when I'm going to clean this up. If I square 1/2 y, that's going to be 1/4 y squared, times another 1/2 gives me 1/8 y squared. And now I've got a dy in here. Doing this the old-fashioned way without a calculator, I have to take my antiderivative. So this bumps up to an exponent of 3. Dividing by that, we have 1/24 y cubed, integrated from 0 to 2. I can yank this 1/24 out of there, and inside now I've got 2 to the third power minus 0 to the third power. Well, 0 to the third is gone. 2 cubed is 8, so we have 1/24 times 8, which just reduces to 1/3. So that's choice A. On this free response problem, which is a no calculator problem, we're given this f function defined piecewise right here, and we have this R region that's this first quadrant area bounded by the f function and the two axes. Based off this, our first task is to find the area of R. So I have to figure out which way I want to integrate, left to right or bottom to top. Since I already have this in terms of x, and they're not really requiring me to do anything special, I'm just going to go left to right. So this is basically going to be a left x value and a right x value for my integral, for my limits of integration, and we're doing a top function minus bottom function, which basically just means the f function. The tricky part is the f function changes when you get to 1. So I'm going to need two integrals for this. I'm going to need the integral from 0 to 1 of this first branch here, 2 minus x squared dx. And to that I have to add the integral from 1 to 2 of x minus 2 quantity squared. So let me use my fundamental theorem. Since I can't use a calculator here, I'm just going to take antiderivatives and plug things in the old-fashioned way. For this first one, antiderivative of 2 is just going to be 2x. And then this is going to be 1/3 x cubed that we're subtracting. And that's evaluated from 0 to 1. Over here now, I can basically use my mini substitution rule, I like to call it. So antiderivative reverse power rule would bump this exponent up to a 3, and then we'd have a 1/3 out in front dividing by 3. We'd have to divide by the derivative of this interlinear function, but the derivative is just 1. So this just comes out to 1/3 x minus 2 quantity cubed, and that's also being evaluated from 1 to 2. Now, alternatively, if you wanted to do more work, you could have expanded this into x squared minus 4x plus 4, and then use your reverse power rule on that as well. But this will be a little bit faster. So plugging stuff in, we've got all the stuff in this first evaluation box with 1 plugged into it, minus this stuff with 0 plugged in. And then over here we have this stuff with 2 plugged in, and we have a 1/3 that I'm going to take out in front just to make my life a little easier. So I'm going to have 2 minus 2 cubed minus 1 minus 2 cubed. Cleaning things up a little bit because I have to, well actually I don't have to clean anything up if I didn't want to. These are all constants, so I could leave it like this and just move on, but I mean, what fun would that be? It's not the real AP test I'm taking right now, so I'm just going to simplify for the fun of it. So for this first group of stuff, I just have 2 minus 1/3. Okay, that was pretty easy. Over here, these are both being multiplied by 0, so that whole second bracket's just gone. Over here, we've got 1/3 times whatever happens inside this bracket. 2 minus 2 is 0, so that's gone. Over here we have 1 minus 2, which is -1. Cubing that keeps it -1, but then we're negating all that, so it becomes +1. So we have plus 1/3 times +1, so plus 1/3. And we get even more good news now. This actually isn't so bad to simplify. Negative and positive 1/3 cancel, leaving us with just 2. For this part of the problem, we're told that region R is the base of a solid, and for this solid, each cross-section perpendicular to the x-axis is a square, right? But don't evaluate an expression with one or more integrals, it's going to be more than one, that gives the volume of our solid. So I essentially need to get an area formula for the cross-section of this solid, and then just integrate that area formula over the interval from 0 to 2. And it's going to be 0 to 2 this way because they said we were perpendicular to the x-axis, so this is x integration we're using. So I'm going to have to split this up just like I did when I was finding the area of R. My general formula, since this is a square, is going to be a of x equals s squared. But now the thing I'm squaring, that's just going to be the distance from one end of the region R to the other, so from the x-axis to the function itself, which is to say the side of the square here is just going to be the function. So I have my volume equaling an integral from 0 to 1 of basically 2 minus x squared squared. 2 minus x squared by itself is just giving you one side of the square, so you just multiply that by itself to get the area of the square, and don't forget your dx there. Plus we have an integral from 1 to 2 of this other rule squared dx. They said we didn't have to evaluate it, and I just did squared squared, so that gives me the 4th power there. They said we didn't have to evaluate it, so this is just done. For this last part of the free response, they're saying the portion of the region R between x equals 1 and 2 is revolved around the y-axis now to form a solid, and we want the volume, and this is not even a right, but don't evaluate. We want an integral for this thing, and we have to evaluate it. So because we're going around the y-axis, integrating with respect to y, I'm going to start by rewriting this rule here, which is the one we're using because this is 1 to 2. I'm going to rewrite this as x equals something with a y in it. I can do that by square rooting both sides, so I have radical y equals x minus 2, and then I can write x equals radical y plus 2. Now, since I'm going around the y-axis and there's this gap between this little part of the region here and my axis of revolution, I'm going to have to use washers on this one. So I have a of y equals pi times big R squared minus little r squared. So in this case, big R is going to be the distance between the outer edge of my bounded region and the axis of revolution. So that's just going to be this radical y plus 2 function, which I'm actually going to rewrite as y to the 1/2 plus 2, and that's going to be squared because it was big R squared. Why did I rewrite it like this? Well, I know I'm going to have to integrate this somewhere down the road, so might as well make it a fractional exponent. Now, little r, that's the distance between this inner part of the bounded region. Remember, this is just the region between 1 and 2 of this overall r here. Too many r's in this problem. So this inner radius is just going to be a constant fixed distance of 1 from the axis of revolution, the y-axis. So I'm subtracting 1 squared. So then it's time for an integral, it's time for some simplifying, it's time for some limits of integration. Since I'm integrating with respect to y, I have to go from bottom to top with my limits of integration. On the bottom, I've got y equals 0. On the top, right here, what y value is this going to be? It looks like it's going to be 1. If I want to find out where this function equals an x value of 1, well, let's see here. If I square both sides, no, wait, if I want to solve for y, I have to subtract 2 first. So I have 1 minus 2 is negative 1. Then I square both sides to get 1. So yes, we're going from 0 to 1. Now, while I'm at it, also to make my life easier, notice I pulled this pi out of the integral. I usually do that on these. And inside now, I'm just going to have the stuff that was in this parentheses. So I'm going to expand this a little bit. Otherwise, it's going to be quite a nightmare to try to integrate this. So I'm going to use a squared plus 2ab plus b squared to expand this squared binomial. So I've got y to the 1/2 squared, which is just going to be y to the first power, because you have 1/2 times 2. Then I have to multiply these together and double it for the middle term. So that would be, let's see, 4y to the 1/2. And then I've got 2 squared, but I've also got this minus 1 that I'm subtracting from it. So that's a grand total of 3. And the antiderivative of 3 with respect to y is just 3y. And I have my dy here. All right, so that's actually just 3. I'm going to leave that in there for now. I'm about to take the antiderivative, though. I'm getting ahead of myself here. So now let's go and take the antiderivative. I've got the pi out front. This is going to be 1/2 y squared. This bumps up to a 3/2, so we're multiplying by 2/3, so 8 over 3 y to the 3/2. And this now is going to be a 3y. Now I can turn it into a 3y. This is evaluated from 0 to 1, so I have pi times all this stuff with 1 plugged in, minus all this stuff with 0 plugged in. And that's in a big parentheses with a pi outside. All the stuff with 0 is just gone. I mean, I don't have to simplify here, but I'm going to. All the other stuff now, we just have 1/2 plus 8/3 plus 3. And that's with a pi outside. Getting a common denominator of 6. This is 3/2 plus 16, or rather 3/6 plus 16/6. That's going to be 19/6 plus 18/6. 19 plus 18 is 37 over 6. So 37 pi over 6 is as simplified as this thing is going to get.